All right, well, welcome to another beautiful day of statistics class. Believe it or not, guys, we are 2 weeks away from being done. Our final exam is actually 2 weeks from today. So, holy cow, this quarter has flown. Before we get going into questions about homework and stuff like that, I just want to let you know about some changes that I've made on due dates. Chapter 11, because we're kind of in the middle of it, I didn't want to make it due tonight, so I've actually extended it to Thursday. So Thursday the 11th. So you're going to have 2 more days to work on the chi-square stuff. So the plan today is we'll finish talking about chapter 11. I'll show you the other applications of chi-square. You'll see that they're all really similar, and you do the same kind of thing with the calculator, but I wanted to make sure that you guys saw what to do and how to do it before the homeworks were due. So that stuff's actually going to be due on Thursday. So because I bumped all those homeworks to Thursday, and you got this project thing, I went ahead and bumped the project to Tuesday. So the project is now due a week from today instead of on Thursday. All right, so bought you guys a couple more days to work on that. Again, things just kind of got all slid around, but I figured better to give you guys a little bit extra time. All right, so just be aware of those changes. Those have been made on Canvas, so you will see them. Obviously, it's different than what the syllabus says, but the Canvas dates now will show that those changes have occurred. All right. So anyway, so those are just some shuffles of dates. And so my plan today is to go ahead and finish chapter 11, show you some other uses of chi-square, and then we'll start into chapter 12, but really it's going to be an algebra review. We're going to review, you guys, a little bit linear functions, because linear functions are going to be super important when we get into chapter 12, which is about regression. All right, so that's my plan. But as always, I'm more than happy to talk about any homeworks or anything. So is there anything outstanding that you guys would like to look at or talk about?
Can we go over question 6 of chapter 11, goodness of fit?
Okay, number 11, goodness of fit. And you said that was number 6, Ashton?
Yeah.
Okay, I put that on the list. Anything else?
Yes, can we look at question 1 from Independence, chapter 11?
Yes, we can, but we're going to look at that after we talk about independence, because we haven't talked about the how to use chi-square to test independence yet.
Oh,
So, because we didn't really, that was right about where we left off, right? Actually, did we do an example? I honestly don't remember. I don't think we did. So what I want to do for that, Bruno, is I want to go over a couple of examples with independence, or the test for independence, how we use chi-square, and then we'll go back and look at number 1. Okay, so we will do that, just not right now. Remind me when I get done with that. If I don't come back and address that, let me know. All right, but I'll put that on the list, and we'll do that later. Yes, matrices. It turns out it's a lot easier if you put stuff in as a matrix in the calculator. So I'm going to show you guys. And
yeah, no. I figured it out from the homework. I mean,
it's not as bad as you know.
Trouble. We had to do the trouble of actually physically putting it through and everything.
Yeah. All right. Okay, well, let me go ahead then and share my screen. We'll go and take a look at that guy. Give me 1 second here to actually get things set up. All right. Okay, let me go ahead and we'll jump over to our class page. So let's go look at the assignments. And we'll jump down to chapter 11, and it was goodness of fit. And Ashton's request was number 6. Okay, so it says here, a recent national report states the marital status distributed of the male population age 18 or older is as follows. 32.1% have never been married, 54.6% are married, 2% are divorced, or sorry, widowed, and 11.3% are divorced. Okay, so we've got this information from, whatever entity has done this research, right? And so now we do a random sample of 1,900 adult men from California, and we got these numbers, right? So of those 1,900, we have 590 of them have never been married, 1,082 are married, 32 are widowed, and 196 are divorced. All right, so what we want to do first, it says complete the table by filling in the expected frequencies. So basically, when asking these 1,900 adult men from California, how many of them do we expect to have never been married? All right, well, that's where we're going to use that percentage, these percentages that we have, because we need to figure out what is 32.1% of 1,900. What would that mean for there to be 32.1%? So this is actually pretty easy to do. We'll take 1,900, so crack out a calculator. You're going to take 1,900 and you're going to multiply it by 0.321. So what I'm going to do here in the box, I'll type what I'm going to put into my calculator. So I've got 1,900 times 0.321. The 1,900 came from the fact that that's how many men we're sampling, right? That's our sample size. And the 0.321 is the 32.1%. All right, so when I actually do that, my calculator tells me that that's 609.9. All right, so there's that guy. So now for married, we're going to do the same thing. We're going to take that 1,900, but we're going to multiply by the 0.546, because that's the percentage that are married. And so I got 1037.4. And thanks, Tassel, by the way, for giving me those numbers in the chat box. Okay, so widowed, it's 2%. So that's going to be 1,900 times 0.02, which is 38. And then divorced, 11.3% of 1,900. I got 214.7. All right, now obviously we can't have decimal number of people, right? But since the expected is really, we're just measuring against that, we're going to go ahead and leave these as decimals. But just looking at these numbers, what do you think? The actual frequencies that we got, how do those compare to what we should expect according to the US population? Close? Far off? What do you think? Because that's what we're trying to do, right? We're trying to test the claim that the distribution from California is as we would expect from the national numbers. And I mean, I don't know about you guys, these don't seem that far off. 590 versus 610, 32 versus 38, 1,082 versus 1,037. So it looks kind of decent, but remember, that's not good enough for us. We need the, yeah, but what about at this level? So let's test this at the 1% significance level. All right, so before we go to a test, are we good with how to get the expected frequencies? We're just taking our sample size times the percentages we expect to see. All right, so what test are we going to use? Well, this is going to be a goodness of fit test. Now, they give us all these options. How do we know that it's goodness of fit? Well, one, you could say, well, we're from the section called goodness of fit, but remember on an exam, we're not going to be told that. So what about this tells you that this is a goodness of fit test?
The outcome and the expected outcome?
Yeah, that what we've got are expected values, and we're comparing our values to an expected set, right? So goodness of fit is all about, is our sample distribution the same as the expected distribution? Okay, so anytime we're comparing our sample numbers versus expected numbers, that's goodness of fit. All right, so that's how we know that that's the test we want to use. All right, so what are the null and alternative hypotheses? All right, so our null hypothesis is going to be that our distribution in our sample, so our California distribution, is the same as national. Okay, so we're going to click this one right here. The distribution of marital status in California is the same as it is nationally. Remember, the null hypothesis is always an equals, and that's basically what we're saying here. The distribution in California equals the distribution nationally. So then that means that the alternative hypothesis is going to be the distribution in California is not the same as it is nationally, right? So we're just looking for, is it different? So null hypothesis, they're the same distributions. Alternative, they're different distributions. And that's always going to be the case when we're doing goodness of fit. Like anytime you have a goodness of fit problem, you can, and you wanted to write out null hypothesis, you can immediately just write the distribution is the same. Alternative, the distribution is not the same. So that's another good thing about goodness of fit, is you don't really have to think about the null hypotheses, right? Think about all those other tests that times we did tests, and you know, we were doing our hypothesis testing, and we had to put in the mean is not equal to, the mean is greater than, the mean is less than, right? Or the proportion is greater or whatever. Like we had to pay attention to which one it was. This time, nope. Goodness fit is either equals or not equals. Yay. All right, so there are those. So now degrees of freedom. Ooh. Does anybody remember how to determine degrees of freedom?
Like all the categories minus one?
Good.
Or added up together minus one?
Yep, that's exactly right. So we count up the number of categories, not the number of people, not the sample size, but the number of categories, and we subtract one. So we had 4 categories, right? Never married, married, widowed, divorced. So that means our degrees of freedom going to be 3. Now, that's super important because when we go to actually do the test, we have to tell it how many degrees of freedom. Just like with the student t-test, right? So we always have to calculate our degrees of freedom. And for the goodness of fit, it's always take your number of categories and reduce it by 1. All right, well, now we're ready to go to the calculator. So before I do that, let me just come back up here and copy these numbers real fast, because I want to do this in a calculator. I don't want to do it by hand. All right, so I got our numbers. so let's go to the calculator. So I'm going to switch my share here. Go to the calculator. All right, so when we do goodness of fit, the first thing we need to do is put our information into a list. So I'm going to go to stat, and I'm going to do edit. And so I'm going to put the information in the list. So let's start with what we observed. So there were 590 never marrieds, 1,082 marrieds, 32 widowed, and 196 divorced. Okay, so that was the data that we were given. Now, then I'm going to arrow over here and I'm going to put in the expected values that we calculated. So we expected 609.9 for the single, the 1037.4 for the married, 38 for widowed, and 214.7 for divorced. So you always want to put in one list of your observed, the actual sampled values, and then the other list of what we expected to see, the expected values. All right. So now that we have that, let's go to stat. All right. And we're going to arrow over to tests, because that's where the chi-square goodness of fit is. And arrow up here to chi-squared goodness of fit. All right, so I'm going to hit enter. So my observed was in L2 and my expected was in L3, so those are perfect. But I do need to change my degree of freedom, because this one, the degree of freedom was 3. So now we'll go down here and we'll calculate. All right, so here's the important numbers. We've got our chi-squared. That's the test statistic, is 5.142856, blah, 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 blah. All right, and then we've got a p-value of 0.16163, blah, 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 blah. Right. But that's what we're going to put in to our homework set. So let's go back over there. All right, so our test statistic to 3 decimal places was 5.142. Maybe you remember, I don't know if you remember, but the bigger chi-squared is, that's the smaller your p-value, and therefore the less likely that we're going to, or the more likely we are to reject our null hypothesis. So because the chi-square was coming from E minus O, expected minus observed, and then we squared it. So if that's big, that means the differences are large. So the fact that this is only 5 something, that's not very big. The p-value, we were given 0.1616. And this is really what matters, the p-value, as opposed to the test statistic when we go and we do our hypothesis test. Because now we want to compare that to alpha, and we were at the 1%. Yeah, the 1% significance level, 0.01. So that means my p is bigger than my alpha. All right, so what do we do when p is bigger than alpha? Every time, what do we do? You only have 2 choices. You can either reject the null hypothesis or you can fail to reject it. What's it going to be? I know somebody remembers. Come on. What do you do if P is bigger than alpha? Do you reject it or fail to reject?
Fail to reject.
Good. We're going to fail to reject the null hypothesis. We don't have enough information to say that it's not the case. So remember, the null hypothesis, we come back up here, was that the distribution in California is the same as it is nationally. We don't have enough evidence to say otherwise, right? We can't reject that. So when it comes down here, let's just see what we got. So there is sufficient evidence to conclude that the distribution in California is not the same as is nationally. Nope, that's not true. There is insufficient evidence to conclude that the distribution of marital status in California is not the same as it is nationally. There's sufficient evidence to conclude that the marital status and residency are dependent. No, we're not testing dependence. Sufficient evidence to conclude that the distribution of marital status in California is the same as it is nationally. That's close, but that's not quite right. I mean, here we're saying we're accepting the null hypothesis, right? And then there's insufficient evidence to conclude that marital status and residency are dependent. Okay, again, we're not testing dependence. So this one, we're going to click this guy. There's insufficient evidence to conclude that the distribution of marital status in California is not the same as it is nationally. Right? I mean, we can't say for sure that it is the same, but we're basically saying, well, we can't say that it's not the same. And I know that feels weird, and you probably still don't like this failing to reject business, but that's how hypothesis tests work. All right, so I think that was Ashton that asked about that. Is that better for you, Ashton? A little clear what you need to do for this kind of problem?
Yeah, thank you.
Okay, cool. You're very welcome. All right, so goodness of fit, one of the uses of a chi-squared test, and it works pretty well. All right. So Willie, you just said, is the chat box working? I would say yes, but I guess I wasn't seeing it, huh? Thanks, guys. As I'm like, I know somebody's got to know, and everybody's responding. Yeah. Anyway, sometimes when I'm in share screen mode, the chat box doesn't work all the time. So, thank you. I guess it is working. All right. Okay. So there you go. There's the goodness of fit version of chi-square. All right. So what I'm going to do is I'm going to go ahead now and show you some of the other things that we can use the chi-square for, some of the other tests. And I mentioned that there are two other big ones that we use. So let me just go ahead and dive in there and show you the test for independence. So I'm actually not going to hop up to the whiteboard because I'm in a new space for a couple days and there's no good space for the whiteboard. So we're going to do this just via the computer whiteboard, but it should feel fairly similar. All right. So goodness of fit works really, really well. And just to kind of remind you what was going on there when we calculated our chi-square. So it's right here. So goodness of fit. The chi-square number was found by adding up the differences between the expected and the observed, and then dividing that by the expected. So think about that example we just did where we were looking at the marital status. You would take, say, like the divorced, or another, the widowed. We expected 38. We actually observed 32. So you would take the difference of those as 6, squared is 36, divide that by the expected, which is 38. So you get 36 38ths from that one. And then we would add that to the same result from all the others. And that's how we got our chi-square. Okay, and it was all about that number in terms of the degrees of freedom, whether or not we end up accepting, or sorry, rejecting or failing to reject. All right, now, when we do the test for independence, it's exactly what it sounds like. When we have a test for independence, we're looking to see, are two different things, two different variables, independent? All right, and so the null hypothesis always for a test for independence is that the two variables are independent. So that means, of course, that the alternate hypothesis is going to be that the two variables are dependent. Because if you're not independent, you're dependent. All right, so you can see how this is very different than goodness of fit. Goodness of fit, we were looking at how does one how did our observed distribution match up against our expected distribution. This time we're looking at just, are things dependent or independent? Now, you may remember we talked about this back when we did probabilities, right? If two variables are independent, then one of them does not affect the other. Well, that's exactly what we're testing here. It's just we don't necessarily know the exact probabilities, so we can't do things like what's the probability of one dependent on the other, or one given the other, and all that kind of stuff, right? But we can still determine whether or not, well, we can see whether or not there's evidence to suggest that they're actually independent or not. Okay, so here's what we're going to do. Let me give you an example. Let's say we're going to look at, box that over here for a second. But let's say we're looking at the women that are in the military. Okay, so women in the military. And we're going to look at the 4 branches. So we've got Army, Navy, Air Force, and Marines. And what we're going to look at is actually in each of these branches, how many women are officers versus how many women are enlisted. Okay, so I've got some numbers here. These are completely made up numbers, so don't be like, oh wow, I had no idea that there were 10,791 officers and female officers in the Army. I have no clue how many there actually are, but these are just some numbers. All right, so suppose we go out and we count and we find that there are this many officers and there are a little over 62,000 enlisted women in the military, or in the Army. So then we go to the Navy, do the same thing. You see 7816 and 42,750. In the Air Force, there are 11,819 officers and 54,344, not 59. 54,344. And in the Marines, there are only 932 officers, and there are 9,525 enlisted females. All right, so here's how the test for independence is going to work. In this case, is we'd be wanting to see is the number of officers and enlisted, does that depend upon which of the groups you're in? All right, so is there some sort of a dependence between branch of the military and number of officers and number of enlisted? All right, so we don't have a distribution we're trying to fit to. So it's not goodness of fit. But we are looking to see, are these things, is officer versus enlisted dependent upon which branch you're in? Okay, so it's a very different kind of question, and yet we're still going to use the goodness of fit. We're going to use that goodness of fit chi-squared idea, and in fact, our chi-squared is still going to be the same E minus O squared over E. It's just this time we're going to do this for each one of the entries in our grid here. So there are actually going to be 8 of these numbers we're going to calculate for this chi-squared. Okay, but now you're starting to go, okay, well, that's great. Those are my observed. Like all of these numbers in here in this grid are our observed numbers. How the hell do we get our E? How do we get our expected? Well, the way that you get your expected is this. The expected value is going to be the row sum times the column sum divided by the total, the grand total. Okay, now this is why we're going to want to use matrices, because I just want you to think about what we'd have to do to calculate the E's. Let's just say we're just going to calculate one of them. Okay, let's calculate the E for Marine officers. So that's just for this one right there. Here's what we'd have to do. We'd have to first take the row sum. So that's going to be 932 plus 9525. Then we're going to have to multiply that by the column sum. So we'd have to add up all the officer numbers. Okay, so that would be times 10,791 plus 7816 plus 1189 plus 932. And then we'd have to divide that by the total of all 8 of these numbers. So I'm going to clear sum of all 8 values because I'm too lazy to try to write them out. Plus I don't have enough space. So this calculation would give us the expected number in this box. Then once we have that expected number, we would find the difference between that expected number and what's observed, square it, divide by that expected number, and then do that again for every other one of these entries. Okay, so you can probably see now why we don't want to even attempt to do this by hand. We want to let a calculator do it for us. But here's the real question. Why this formula? where is this formula actually coming from? And it turns out that that was the formula that we had for probabilities of independent events. If you go back way to like, I don't know, it was like chapter 3 or something forever ago, probably back at the end of January or something, when we were talking about conditional probabilities, when we did independent events, this is the formula. This is how it would play out if you looked at those probabilities and built it in terms of the entries in the grid. So it's a blast from the past where this E comes from, but we'd have to do that for every single one of these entries. And nobody wants to do that, right? Nobody wants to have to do that for all of these things. It's kind of a pain. So let me show you how we can use the calculator to help us out. All right. However, before we get there, I just want to talk about one more thing before we try to jump to any kind of a chi-square test. Remember, what we need to know is the degrees of freedom. And in this case, degrees of freedom are calculated in a slightly different way. Because now we don't have just a certain number of entries or groupings that we can just take away one from. But what you're going to do is you're going to take the number of rows minus 1 times the number of columns minus 1. So like in this example, our degree of freedom would be number of rows is 4 minus 1 is 3. Columns, there are 2 minus 1 is 1. So we get 3 times 1, which is 3. All right, so the next logical question is probably, why do we have to calculate degrees of freedom differently? And the answer to that is because we're doing a different test. While yes, we're using the same distribution, it's coming from a different place. And that's why we have to have this set up like that. Really, if you think about it, remember what we did before when it was just like a column of numbers. We took the number of entries in there minus 1. Okay, so that's already this like row minus 1 column, or column minus 1 idea. So, well, if we have to apply that to both rows and columns, it kind of makes sense. All right, so let me show you how we can use the calculator to take care of this all at once for us. And it is going to bring back Bruno's favorite, the matrix. So let me go to the calculator and let me show you how this works. Okay, so first of all, matrices. You can find them. If you look here, you'll see where it says matrix, the secondary command. So I'm going to do second matrix. Now, this has space for all kinds of matrices. They're named by their letters, so matrix A, matrix B, C, D, and so on. But what we're going to do is we're going to edit. We're going to change this matrix. I'm going to recommend you always just change matrix A, so that way you're just always using the same matrix every time you do one of these calculations. But if you want to go down, arrow down, and do another one, that's fine. All right, now the first thing you'll see up here are 2 numbers with an X in between them, right? So there's a 2 and then an X and a 3. And that's giving you the dimensions of this matrix. The first number is the number of rows. It's how many rows we have. So you notice that right now this is a 2 by 3 matrix. So there are 2 rows. The second one gives you your number of columns. So there's 3 columns. So the first thing you should do is adjust this so that it's going to hold your data. So when we were looking at that example from the women that serve in the armed forces, there were 4 rows. There was Army, Navy, Air Force, and Marines. All right, so there's a 4. I'll hit enter so that it moves me over. Notice that the matrix just changed, so there are 4 rows. And then we needed 2 columns because there was the 1 column for enlisted and the other for officer. Okay, so I'll hit enter. And so notice that this matrix now is the right size. It's got 4 rows, 2 columns, and now I can put in my information. So I'm going to go ahead and type those numbers in. So we got 10,791. That was the number of Army officers. And the enlisted was 62,491, and so on and so forth. So let me just go ahead and punch these in. All right. So there is all the information that we already had. And oh, and by the way, all you got to do is hit enter and it moves you to the next one. So it moves across the row. And then once you get to the end of the row, it drops you to the next column or down to the next row, go across and so on. So it can be pretty fast. Just keep hitting enter every time you put one of them in. All right, so there's our matrix. There's our information in there as a matrix. So now what we're going to do is we're going to go to stat. Again, we're going to go over to test. And this time we're going to use the one that's just chi-squared test. Before we were using chi-square goodness of fit. This time we're going to use the chi-square test. Now, when you do the chi-square test, it's going to ask you for your observed matrix. All right, well, we put that in A, so it's going to know that that's our observed matrix. Now, the second row, the second line here where it says expected, you don't have to create the expected matrix. It will do that for you. And so what it's going to do is actually store that in B. So remember that horrible thing I was writing out where we had to add up the row numbers and add up the call numbers and multiply them together and then divide by the total, blah, blah, blah. It's programmed to just do that, to actually calculate the expected values. So you don't have to worry about that. It's going to store it there. We'll go look at it in a minute, but I'm just going to go ahead and store it in B. Now, you may notice that there's also something else missing on this. What's missing on this little bit of a window that was in the goodness of fit window? What don't we have to enter here? Anybody notice what it is?
The degree of freedom.
Yeah, the degree of freedom isn't here. Well, that's because the calculator is smart enough to figure it out. It's going to look at the matrix and it's going to reduce 1 from the rows. It's going to reduce 1 from the columns, multiply those together. So it already knows how to calculate that degree of freedom. All right, so this is quite excellent because now that we've put all that stuff into A, we don't have to do anything other than hit enter. All right, so it thinks for a little bit, and here are the test statistics. So we've got our chi-squared, 654.27, blah, 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 blah. We've got our p-value, 0. And then the degrees of freedom is 3. Well, you may remember that we calculated the degree of freedom should be 3. So like I said, it already knew how to do it. All right, so now let's analyze what this tells us. So that chi-squared is a big number. I remember the chi-squared, it's looking at the difference between the expected and the observed. So the more that difference is, the greater our chi-squared number is going to be. Okay, so we got a pretty big chi-squared. And if you look at the p, you may not actually like this, because you see that p and it just says 0. What the? Isn't it supposed to be point something or other so we can check it against a percentage or whatever? Okay, well, this is so small that the calculator rounds it to 0. Okay, it's not going to be 0. It's going to be 0.0000, a bunch of zeros before anything else comes. But remember what this p tells you. The p is the probability that we would get this distribution if the null hypothesis were true. All right, so if the null hypothesis was true, the numbers we actually had are so incredibly impossible. Like, if you got those numbers, you would be completely blown away. You'd be like, how the hell did that happen? The probability is so small, it shouldn't have occurred, right? It's like oh yeah, you tossed, a head on a coin 100 times in a row. What are you going to think? You're going to think, oh, that's not a fair coin. Something funky's with it. Well, that's exactly this. This is making us think that null hypothesis, that's probably not right. Okay, so our null hypothesis, we are going to go ahead and reject the heck out of that because the p is less than alpha. So you may remember, let me go back to that screen just so you guys can see it again. That what the null hypothesis is for test of independence is that the variables are independent. So with this data set, we saw that we are going to reject the null hypothesis. We think very much that it is not true that the variables are independent. So statistics, this data right here is more than sufficient statistical evidence for us to throw away the null hypothesis. And so what we know is that the distribution of officers and enlisted men, or sorry, enlisted women, and it's not independent of service. It actually depends which service you're in, how the distribution of officers and enlisted are. But you can already kind of see that. I mean, look at the Marines, for example. There are 10 times as many enlisted female Marines as there are female officers. You don't see that in the others, right? Like in the Air Force, it's like not quite 5 times, right? This one's 6 times, this one's 6 times. So there's a little bit different a distribution that you can already kind of see. But statistically, because of the fact that that P was 0, we're good. All right, so Will, you said we don't even need an alpha. Yeah, for this one, pretty much any alpha you were to give me, I would give you the same answer, right? Like when we say at the 10% level of significance, at the alpha equals 0.05 level of significance. For this one, I'm just going to tell you at any level of significance, it doesn't really matter, right? So do we need an alpha? Again, you should have an alpha. Like I've talked about before, we should always have an alpha to start with. And then we make our results based on, or our conclusion based on that. But for this specific example, because P is 0, yeah, it doesn't matter what the alpha is. You could have told me be at the, 1/100th% alpha, and I'm still going to come back to you and go, yeah, that null hypothesis is garbage. We're going to throw it away. So this is a situation, man, if you ever get a P of 0, So let's say you're doing this for something in your job in your future class, and you do some sort of a test and you get p equals 0. The first thing you should do is maybe just double check that you didn't make a mistake, because that's kind of rare. But if you do get p equals 0, that's a great thing, because you're going to be supremely confident in your decision to reject the null hypothesis. Right? Like, think about those ones where, let's say we're at the 10% level and you get, 9.8%, or you get 10.1, and you're like, man, it is just so close to that 10%. I really don't feel good one way or the other, whichever side I'm on. This one, oh man, we're so far away that we can feel really confident that we're far under the alpha, and therefore we can really be good with rejecting the null hypothesis. All right, so I'm going to do another example of this, but I just kind of want to point out a couple things before I move off of this screen and erase it. I just want to show you that, I mean, you can see why we're using the chi-squared again, because we're looking at how far off are we from what we expect. It's just what we're expecting is the value we would get if they were independent. Go back and look at your probabilities, and you'll see that like conditional probabilities, there was a formula that involved multiplication and all that, and that's what this is coming from. But it's really kind of the same idea. We're still trying to fit it to an expected distribution. It's just the expected distribution is coming from independent probabilities. All right, so let me show you another one. And you'll see that it can go really fast now that we've talked about it and you know what to do. It can go pretty quick. So let me just go ahead and clear everything here. So let's say we go and we ask, asked, how about we ask? All right, so we go and we ask people their sport preference. All right, so we just going to say, okay, so hey, out of these sports, which do you prefer? And what we're curious about is this dependent on having graduated college? So the question is, if you graduate from college, are you going to have a different preference when it comes to sports than someone who hasn't graduated from college? So we go and we do a test. We do a sample. And so our two groups are the college grads and the non-grads. Okay, so there are two groups. And we ask them, all right, which of these is your favorite sport? I would say football, baseball, and just because, why not put in curling? Okay. And I know some of you are probably like, curling? Never even heard of that. It's in the Winter Olympics. Sport or not, I think you could probably have an argument against it, but we're going to put it in there. I happen to really like watching curling. It drives my family crazy. When the Winter Olympics are on, I have the curling channel on all the time, and they're like, God damn. Anyway, so here we go. So let's say we go and we ask a bunch, and so we find that there were 18 for football, 10 for baseball, and 4 for curling from our college grads. Okay, so we went and we asked 32 college grads and got these numbers. And then for non-college graduates, we got 20, 16, and 12. All right, So we just went out and asked a whole bunch of people, which of these is your favorite sport? Football, baseball, curling. They gave us our answers, and then we said, oh, and can you tell them, did you graduate college or not? All right, so let's see if these are independent. So, so we're checking to see if this is dependent. So this is a test for dependence. So the null hypothesis is going to be that sport preference is independent of college. I'll put your college education. So that means that our alternative hypothesis is that the sport preference is dependent. We're going to put here dependent on college. So test for independence, always the null hypothesis is independent, that these two things are independent. All right, and let's set an alpha. Let's use an alpha of, let's go with 0.1. Okay, so we'll go at a 10% level, because it's not very important if we're right or not about this. It's not like the world's going to end if we make a incorrect assumption here. So let's go with 10%. All right, so there's all our information. Let's go ahead and use the chi-square test, and we'll go ahead and use matrices. But before we get there, what's my degree of freedom here? What's the degree of freedom for this one? And I can see the chat box, by the way, so you can go ahead and throw it in there. I know we don't need to decide it because the computer will tell us, but let's practice it. What's the degree of freedom here? All right, good, Tassel. Tassel, just put 2 in the chat box, right? Because we take the number of rows minus 1 times the number of columns minus 1. So that's 1 times 2, or 2. So this one, we're going to use the chi-square with degree of freedom 2. But like I said, the calculator will already do that for us. All right, well, let's go see what the calculator has to say. So again, we're going to start by putting our information into the matrix. So I'm going to go to matrix. I want to edit. I'm going to go ahead and edit. We'll just use A again. This time I need to change it so that it's got 2 rows and 3 columns, right? Because the 2 rows were college grads and non-college grads, and the 3 columns were football, baseball, and hockey. All right, so let's see what we get. All right, so we've got, there were 18, 10, and 4, I think were my numbers for our college grads. For our non-college grads, we have 20, 16, and 12. All right, so there's our matrix A. So now we got our matrix. Let's go to stat. Go arrow over to tests. We're going to come up to chi-squared. We still have our things in observed A. They'll put expected into B, and we'll calculate. All right, so there are our numbers. We got a chi-square, or test statistic, of 2.385, a p-value of 0.303, and again, degree of freedom is 2, as we expected. Oh, I meant to show you. Well, let me wrap this up, and then we'll come back. All right, so there's our p-value. So let's go back to the whiteboard. see what we know. All right, so we just found that the P was 0.303. So what does that tell us to do? Are we going to reject or fail to reject?
Fail
Good.
to reject.
Good. Yep, we're going to fail to reject. All right, so this is fail to reject. So what this means is that we do not have sufficient statistical evidence to say that sport preference is actually dependent on college education. Right? We don't know that it's not independent. All right, so we just don't have enough information at this point statistically to decide to say that, yeah, if you go to college, you're going to have a different preference in sports. All right, so there you go. There's another test for independence. So you can see that it's pretty easy. It's just a matter of putting it into a matrix and letting it do its thing. But what I was reminded about, and I want to show you, I want to go back to the calculator. I want to actually show you the other matrix. Because remember how there was always the expected got put into B? Let me show you that. So I'm going to go up here to matrix again. So the second matrix. I'm going to arrow down to B, and I'm just going to hit enter. Okay, so I just brought it to my window. So if I hit enter on that again, it actually shows me this matrix. So this was the expected value matrix for the sports data. If you actually look at what you should get using that formula of add up the row, multiply that to the sum of the columns, divide by the total number of everything, these are those 6 expected values. So if you ever want to know those, it's actually really easy. You can just go to matrix, highlight the matrix you want, hit enter, and then enter again, right? But if they actually were independent, we would expect 15.2 college graduates to say they like football, and 10.4 to say they like baseball, and 6.4 that said they like curling. And then these would have been the numbers for our non-college graduates. 22.8, 15.6, and 9.6. And so if you go back and you look at the actual values we found, you can see why we failed to reject. Like if you look at the non-college grads, the numbers, the observed values we saw were 20, 16, and 12. They're not all that different. The college grads, we had 18, 10, and 4. So since those numbers were awfully close to what should be expected if they are independent, that's why we got a pretty big p-value and why we couldn't throw it away. Anyway, so this is actually kind of nice because you can actually see what those expected values are and compare them against what you had without having to calculate them yourselves. I'm a huge fan of this, right? Have the calculator do the work for you. All right, so how are we feeling about test for independence? Kind of seeing how it goes. Any questions on it at this point? No, we're looking good. I'm seeing some thumbs up. All right, awesome. Okay, so let's do this. Let's take a real quick break. I actually need to get a drink of water real quick. So let's come back in 5 minutes. All right, this will just be a 5-minute break. I've got 4:38 on my computer, so I'll be back around 4:43 or so. And then I'll show you the test for homogeneity. All right, so I'll be back in just a little bit. All right, I'm back. And before we do the test for homogeneity, I just remembered that Bruno had that question from the homework on the test for independence. So let's actually go back and look at that one and put this into practice like you would with the homework. All right. So I'm going to go ahead and switch screens and hop over there. All right, so he asked about question number 1. So here's independence. So check it out. It says you're interested in investigating whether the type of computer a person primarily uses and the type of car they drive are dependent. So the table below shows the results of a survey. So we go ask a whole bunch of people what kind of car they use to commute and what they prefer in terms of their computer, right? Okay, so first question there says, what is the correct statistical test to use? Again, we know it's independence because this is from the section on independence, but we know that it's independence because we're trying to determine whether these two things are dependent. So it says it right there. So we're going to use the test for dependence. All right, so we'll do test for independence. So then what are the null and alternate hypotheses? Okay, so the null, whenever you're doing the test for dependence, is that computer type and car type are independent, right? That's always the null hypothesis when you're doing a test for independence. All right, so then the alternative hypothesis is going to be that the computer type and car type are dependent. Okay, so we got ourselves set up. Now we're ready to calculate all of our statistics, right? We need a test statistic, the p-value, and do all our good stuff. So let me just write this information down here real quick, and then we'll go slap it into the calculator. So I have 94, 96, 44, 98, 107, 33, 137, 120, and 20. Okay. All right, so we're going to go put this into a matrix and do our calculation. But before we do that, what's our degree of freedom? What's the degree of freedom going to be for this guy? All right, good, Willie. It's going to be 4. So rows minus 1 times columns minus 1, since there are 3 of each. Subtracting 1 from each is 2. 2 times 2 is 4. So this one's going to give us a degree of freedom of 4. All right, so let's jump to the calculator. So we're going to start by going to matrix. We're going to edit matrix A. We need to make this 3 by 3. But now we can put in our numbers. So we had 94, 96, 44, 98, 107, 33, 137, 120, and 20. All right, so there's our matrix. So now we'll go stat, test, come up here to chi-square. Our observed is in A. They can put the expected in B for us. We'll go ahead and calculate. And there you go. So we've got chi-squared is 16.88496 blah, blah, blah. And our p-value is 0.0020349 blah, blah, blah. And again, hey, look, degree of freedom is 4. Okay, so let's go put those in. I'll go back to the homework. All right, so test statistic, our chi-square was 5 point, how many decimals? 3, so 5.143 to the third decimal place. And then our p-value to 4 decimal places is 0.1616. All right, so now how does that compare to alpha? Well, if we go back and see what alpha was 1%, 0.01. So our p-value is bigger than that, which tells us we should fail to reject the null hypothesis. Okay, so there's which of these are we going to do? Well, we're going to go, there's insufficient evidence to conclude. Okay, well, let's see. Distribution, no, don't care about that. Let's see. So insufficient evidence to conclude that computer type and car type are dependent. All right, I think that's the one we want, right? Because saying that they're not independent is dependent, and we don't have enough information to say not to the H naught, right? We failed to reject H naught. So that's going to be our answer here, right? Again, with the multiple choiceness, the ones that say distribution, we know don't matter. So that's not what we're looking at. This one, sufficient evidence to conclude that computer type and car type are independent. No, that would be saying we're accepting the null hypothesis, which we're not. We're failing to reject it. And then if you look at the last one, there's sufficient evidence to conclude that computer type and car type are dependent. That would be rejecting the null hypothesis, and our number is definitely not there. So we'll go ahead and submit our question. Oh man, what did I do wrong? I must have put numbers in wrong. All right, I must have put numbers in wrong somewhere. I was all excited. I was like, I'm going to get points. I'm going to show off that I know what I'm doing. I'm just pulling up my matrix here real quick to see if what I did wrong. Sorry about this delay, guys. I'm just trying to find out what I did wrong. Oh, I typed in a number wrong. That'll do it. I'm guessing you guys have had that experience a time or two where you type a number in wrong in the list, and then next thing you know, you're getting the red X because your p-value is wrong. Anyway, so, but you see the process, hopefully. It's not that terrible. It's just a matter of putting it in there. And trust me, I know Bruno likes to say, joke around about, matrices. You're going to like the matrix in this situation. It definitely saves you time and all that. Anyway, so I apologize for this stuff, but you can see why the 1x led to more x's, right? Because when I calculate this, if my p-value is now actually smaller than alpha, that of course changes this, which changes this to, there we go. So I guess this is going to be less than alpha, which means we're going to then reject the null. And if we reject the null, then that means that there is sufficient evidence for it to be dependent. And I should be good on all of those now, right? Yep. Boom, boom, boom. So yeah, it all comes down to what your p-value is. Anyway, so hopefully, does that at least kind of clear up what you want to do with this one, Bruno?
Yeah, I did clear up.
Okay. Moral of the story, make sure you put your numbers in correctly, and then you'll get the right p-values. Right.
All right.
Okay, so let's talk about the last test here. The last thing that we can use, that we're going to use the chi-square for. I mean, there are more. There are lots of them. So, and yes, thank you for the support there, Carson. It clearly does happen to the best since it happened to me. Oh, yeah, no. Yes, it does happen to everyone. Which is why you want to go slow and steady, right? Okay, so goodness of fit, it's exactly what it sounds like. We're trying to see how well our data fits a expected distribution. Test for independence, again, we're testing to see if two things are dependent or not, right? Like car choice and computer choice, things like that. Okay, so the last one, this one's called the test for homogeneity. All right, now this is one where the name doesn't tell you what it is. Well, okay, it doesn't tell most of us what it is because we're not used to seeing words like, there's an O in there, homogeneity. All right, so what the hell is homogeneity? Well, if you break down the word, homo is same, generation, creation, right? Homogeneity, what this is saying, or what this is really a test of, is this is a test to see if proportions are the same. So there's a word, homogeneous. In math, homogeneous means that it's kind of distributed the same, it's spread the same. We can say like a population is homogeneous if it's all the same. So homogeneity is a question of, are these things the same? And specifically, we're looking for proportions that are the same. Now, it can be 2 proportions, it could be 3, it could be 4, it could be 100. Okay, but the null hypothesis in any case when we're doing a test for homogeneity is that all the proportions are equal. Okay, so all the proportions are the same, which then means the alternative hypothesis is at least one is different. So if we're in the case of only having 2 proportions, they're either equal or they're not. But if we have 3 proportions, 4 proportions, again, they're either all equal or there's at least one of them that's different. You won't necessarily know which one is different, but you'll at least be able to say, nope, it doesn't look like these proportions are actually the same. Okay, so that's what test for homogeneity is. It's a test on proportions. So again, how do you know that you're going to do this as opposed to the others? Just remember, goodness of fit. We're looking at how do we fit a distribution. Independence, we're looking to see if 2 variables are dependent upon each other. Homogeneity, we're looking for proportions, for percentages. Are percentages the same? Okay, so it's a different kind of deal. All right, now an example. Let me just give you an example here so you can kind of see what we're talking about. Let's say we're looking at births at 3 hospitals. Okay, so we're going to look at 3 different hospitals. And we're going to look specifically at what proportion of them are cesarean section births as opposed to a standard vaginal canal birth, okay? So here are basically our, we've got cesarean versus non-cesarean. And so we go and we look at 3 different hospitals. We'll call them hospitals A, B, and C, but maybe it's like, so this is Barton, this is Carson Tahoe, and this is Renown or something, right? Okay, so we just go and we look. And so we find that at one of them, we have this distribution, 54 cesarean, 56 non-cesarean. At the second hospital, we have 28 and 50. At the third one, we have 39 and 55. Okay, and so here's the question. We want to know, is there a difference in the proportion of births that are cesarean at the different hospitals? So let's go ahead and give ourselves an alpha level. We'll test at alpha 0.05. But here's the null hypothesis. The null hypothesis is that the proportion of cesarean births is the same at all the hospitals. All right, so that's what a test for homogeneity is going to do. It's going to test and see, is this the same? All right, so maybe we're just curious if, you know, if we find that it's not the same, then maybe we want to get into what's the reason? Do we have, you know, obstetricians that are, you know, want to do it more frequently at certain hospitals or refuse to do it as much at other hospitals, right? Maybe it's an insurance thing, maybe, right? But so this would be the first start is, let's see if they're the same. If they're not the same, then let's investigate the reason why. All right, so this is an example of where you would do a test for homogeneity. All right, so now the question is, how do we do it? How's the degree of freedom thing work and all that? Well, this is still chi-square. This is going to be a chi-square. But it's going to be a chi-square where the degree of freedom, it's going to equal the number of columns minus 1. So you'll notice that all of these chi-square things, we always have a minus 1 going on. But if you think about this, like with the idea of the matrix, remember how we found the degree of freedom for the matrix was rows minus 1 times columns minus 1? Well, your rows here, they're always going to be 2. Because if we're looking at proportions, proportions come from a yes or no kind of situation, right? They were always binomial. Because this would be, look at the birth. Was this birth cesarean? Yes or no? There are only 2 choices, right? All right, so since we always have just 2 rows, that minus 1 is just 1. So it turns out that this is actually really the same formula as what we were doing with independence. It's just because of the fact that we only have 2 rows, that becomes just columns. And in fact, this still is sort of a test for independence, right? We're trying to see if the cesarean births, the number of cesarean births is, or a proportion of them is independent of hospital. So really test for homogeneity is just a special case of the test for independence. All right, so because of that, it means we're going to do exactly the same thing that we did before. We're going to take this information, we're going to put it into the matrix, and then we're going to do a chi-square on it. So functionally, you'll see that this is exactly the same. So here we go. Let's go to the calculator. Except I closed my calculator. Give me 1 second here. I think I was so frustrated about the inputting the thing wrong that I just closed it all. All right, here we go. All right, so let's go back to the matrix, and we're going to edit this guy. We're going to edit A. We don't want 3 by 3, we want 2 by 3. Because remember, we only had 2 options, either a cesarean birth or not a cesarean birth. So we put in our numbers, 44, 28, 39, 56, 50, and 55. So we go to stat, test, chi-square. Yes, A, yes, B, blue is fine, calculate. All right, so here we go. So we get a chi-square. So our test statistic is 1.2185, right? And then our p-value is 0.5437499. And again, we see that they told us our degree of freedom is 2, which we already knew. All right, so our p-value is 0.54. So if we go back to what we were doing over here, right, we calculated that p is equal to 0.5437, which is considerably bigger than alpha. Right? Again, this is saying that if the proportions are the same, if the null hypothesis is the same, we would get this kind of distribution 54% of the time if we just were to do this random sample. Well, I don't know about you, but that's pretty often. So that suggests that we don't reject H naught, right? So we're going to fail to reject. So that means that we have insufficient evidence to say that the proportions are not the same. Right? So the null hypothesis is the proportions are the same, and we're failing to reject it. We're going to not say that they're not the same. All right, so it appears that there isn't an issue here with hospital, that there isn't a hospital here who's performing cesareans at a higher or lower rate than any of the other hospitals that we're looking at. All right, so there you go. There's your test for homogeneity. And this can come in all kinds of forms, but it always has to be a yes, no, right? It's got to be some sort of a binomial yes, no, and we're looking at the proportion, we're looking at the percentage in that arena. All right, so one more just for good measure. Let me just go ahead and clear all this stuff off. Suppose that we go and we're curious about this. We're curious if if your annual salary affects your perception of being happy or not. Okay, so here's what we do. We're going to go out and we're going to ask a bunch of people this question. You just ask them a nice and simple, are you very happy? Okay, we can even leave that up to their interpretation, but we're just going to ask, are you very happy? All right, so in terms of our data, there are going to be only 2 choices. They either say, yes, I am, or no, I am not. Okay, but again, we were curious about their financial status. And so let's say that we break them down into the following categories: those that earn less than 30,000 a year, those that earn between 30 and 75,000, those that are between 75 and 100,000, and those that earn more than 100,000. All right, so we go out and we ask and we get these numbers. All right, so the question is the proportion different depending upon which of the economic statuses you fall under? Okay, so again, let's pick an alpha. Let's just go with alpha's 0.1. I'll go 10%. And let's see what we find. All right, so in terms of this one, again, it's a test of homogeneity because we're looking at proportions.